And our area of focus is just to look at hypothesis testing. Okay, hypothesis testing. What is the general idea behind hypothesis testing? So, hypothesis testing is all about testing the validity of the existing statements. So we would say that when a certain scholar or a certain person, uh, postulates a claim or give a claim, they claim that this thing is like this. That will raise questions, from other interested parties. They'll be like, could that be true or not? Okay. So when you are trying to examine uh, the validity of the statement said or the claim given by a person, you're saying that you're testing that particular claim or testing the hypothesis. So that is the general idea behind hypothesis testing. So whenever you have the persons under hypothesis testing, um, you have to be able to identify which one in your question is your null hypothesis and which one is your alternative hypothesis. So the null hypothesis is always the existing claim, okay, that you're trying to disprove or prove. Okay, that is the the claim that you're testing the validity thereof. It is usually called the null hypothesis. So in our question, first example, our first question is a quality controller manager believes that the 12-gram box of breakfast cereal should contain an average or the mean of 6 grams of bran. He measures a random sample of 6 bowls of popular cereal for bran content. Can we suppose that the data yields a sample mean of 5.9 grams of bran and a sample standard deviation of 0.37 bran? Then the question is that does the data suggest that the bran content differs from 6 grams or does not differ? In other words, is that can you test is the claim that the average, okay, the mean for the 12-gram box of breakfast cereal is always 6 grams? That's the question. Is that true or false? So the first thing that you need to do in your question is to detect which one is your mean, X bar. X bar is always the mean that comes from the sample mean. Always you'll be given the sample. You can be given the sample size. And from that sample, you'll be told that after selecting the sample, when this person was trying to prove or disprove the claim, they selected a sample. And after selecting a sample, they calculated for the mean and they found the mean that we usually call the X bar. And in this respect, we're told that the sample mean yielded 5.9 grams. So this is our X bar. And then the other mean that we need to get is the other thing that we need to get is the sample size, N. How do you find the sample size? It is given in the question that the person measured a random sample of 60 balls. So 60 is your N. Then from that, you need to get what is called your mu. This one is usually read as mu, which is basically the average of the claim. In the claim, like the existing claim that is already there that you're trying to disprove has got an average. It has the mean. In this respect, the first claim it comes from the quality control manager who believes that the 12-gram box of breakfast cereal should contain an average of 6 grams of bran. So the average from the claim is what? Is 6 grams. So we have the mu our average to be 6, which is same as our mean. Then from here, what you need is the standard deviation. Our standard deviation is what? Our standard deviation is given in the question 0.37. And once you find your mean to be 0.37, you can now proceed in computing the Z-statistics. How do you compute the Z-statistics? To find X bar minus C, the mu all over the standard deviation divided by the square root of the sample size. Let me just be quick to indicate that you only use this Z-statistics if and only if the number or the sample size is less than what? Than 30. Whenever you have 30 and above, you have at least 30, you use the Z-statistics. That's when you use that. But for the sample size that are less than 30, you use the t-statistics. The t-statistics. It has got the similar formula. The formula is just the same. Standard deviation divided by the square root of n as well. But it's only that the sample size now could either be 20, 14, 10. As long as it's less than 1, you compute the t-statistics. You compute the t-statistics. So now, from here, what we will need to do is to compute our Z-statistics, since the sample size is the sample size that we have found is what? It is you know, it is 60, meaning it is greater than 30. Okay, it's greater than 30. So let's compute into these figures. Let me use just a blue marker so that you're able to see. X bar is 5.9 minus 6. Our mu is 6. Over, we are computing into this Z formula, Z statistics. The standard deviation is 0.37. We divide that by the square root of 60, which is our sample size. Once you do all your computations, you find that your Z is negative 2.09. So you find 0.5 minus 6, or 5.9 minus 6, it will be negative 1.1. Then you divide by the standard deviation, 0.37, over the square root of sample size 60. You get the Z statistics that is equal to negative 2.09. Okay. Once you get the Z statistics that you have calculated, get it in mind that you have calculated the Z statistics, and this is how you calculate the Z statistics. So now you will need another Z statistics. The Z value that you get from the table, it is called the critic Z or critical Z. How do you get the critical Z? The critical Z, you get it from the table. You need your alpha, okay? You need your alpha. What is your alpha? Your alpha is 0.05. Now, somebody is asking, where do we get the 0.05? Okay, 0.05 alpha is always given in your question as the significance level. It is given as the significance level. Sometimes if you're told that, if you're not told that it is significance level, they will give you the confidence level. If they say maybe the confidence level is equal to 95%, it simply indicates that to find the significance level, which is represented by alpha, it shall just be the confidence level 100% minus the confidence level. So we say 100% minus what? 95%, and that gives you 5 what? 5%. 5 divided by 100, that gives you 0.05. That is how you find that. Sometimes it doesn't mean that it will always be 0.05. So that the significance level will be 5%. Sometimes you can be given the confidence level of 99. You're told that the confidence level is 99%. Therefore, to find the significance level, you can say 100% minus 99%, and that gives you 1%. 1%, which is equal to 0.01 as your alpha, your significance level. This is all what you just need. You just need to know how to find your alpha. Identify your alpha. your significance level in the question, then you're good to go and you're fine. Now that we have identified our alpha, in the question it is said that we should always say alpha divided by 2. It is always alpha divided by 2, depending on the question there how it is. Okay, if the question has got the data that is symmetrically distributed, that is to say, if your now hypothesis is that mu maybe is equal to a certain number, then it means that your alternative hypothesis will be mu is not equal that particular number, which means if it is not equal, it can either fall to the right or left of that. That is to indicate that the data follows the normal distribution, which means the right side is equal to the left side. If we say that the right side is equal to the left side, what we try to mean is when you cut here and here, you put your z critical z, just from the basic idea, you get standard normal distribution. Then this simply means that you can have your data maybe falling in this region or that region that is upper z. Once the data falls in this alpha over 2 level, alpha over 2, so that once you add alpha over 2 plus alpha over 2, you just get the general 1 alpha. You always divide it by 2. So you add that plus this confidence level here in between, they should give you 100%. You add these two, this one plus that one, then plus this confidence level that you get here, that you are usually given most of the times, then you should actually get 100%. So as we're just concentrating on alpha over 2, since this data is symmetric distributed, the data is symmetrically distributed, you find alpha over 2. So our alpha, we said our alpha is 0.05. We divide this by 2 since we are finding alpha over 2. This should give us 0.0250. 0.0250. This is our area that corresponds to what? To alpha. Now, observe that the table that we are using is a cumulative standard normal distribution table. So what you do, just say 1 minus alpha over 2, which is 1 minus 0.0250. When you subtract that from 1, you get 0.9750. And 0.9750 is basically the area that corresponds to alpha over 2 from the cumulative standard normal distribution table, 0.9750. So what you do from here now is that this this 0.9750, you're going to look for this area from the table. From the table, you go specifically to look for this area, the 0.975. And so it shall come to pass that we're going to go to our table, specifically looking for 0.9750, this area. So let's go to the standard normal distribution table, and we are here. We have reached to our table. So when you look at the table here, what you will observe is that when you followed in this line, our area is here, right? Our area is here. Our area is marked here. So what you do, you move, when you move to the left, you will find that it is in the line where the z value is 1.9. Then when you move upward, okay, let me write using a red so that you're able to see. This is basically 1.9. When you move upward, you find that it corresponds to the 2 decimal places that are 0.06. You add all these, you get 1.96. Okay, 1.96. Now, this 1.96 is the critical Z. It is called the critical Z. Remember, you had the calculated Z that you calculated when you started, but also need the critical Z, the critical Z. The critical Z is 1.96. So when you write, when you try to graph this data and visualize, you'll understand that I said the Z's are found in these areas, okay? Here in between is 0. So we can put 1.96 here as the critical Z. Even this side, we can put negative 1.96. The main instance or the main reason as to why we are putting negative is because from 0 going to the left, we find the negative values. And that's why we had to give this particular Z critique a negative number. So negative 1.96. And on the positive side, the critique Z is 1.96. When all that is said and done, you're going to compare this critique Z, this negative 1.6 and the negative 1.6, n of them. And we said that this data is symmetric, meaning the right side and the left side is just equal. So our Z that we had calculated was the negative 2.09. If we had calculated that previously. So we found that negative 2.09. So you check where this negative 2.09 will lie. From your own knowledge of the number line, you'll understand that this negative 2.96 lies in this region somewhere here. It will be somewhere here. It will be somewhere here. It lies in this region. So basically, this region after the critic Z is called the rejection region. Okay, it's called the rejection region. Similarly, here after the critic Z, we find the rejection what? Rejection region. How do we make a decision? How do we make a decision? How we make a decision now? We check this value. Where does it fall on this from this number? Okay, if it falls in the rejection region, then we reject null hypothesis. We reject the null hypothesis, which was saying that H naught null hypothesis mu is equal to what? It's equal to 6. So we reject that, meaning the alternative hypothesis, which was the opposite of that, it was saying that mu is not equal to 6. So you reject that. You reject that because it falls in the rejection region. But if this number was falling in this region, we could have failed to reject the null hypothesis, meaning because the Z critique or the Z value, the calculated Z value, would have fallen into the what is known as the acceptance region. Okay, then you fail to reject it, the null hypothesis. So now, since this negative 2.90 falls in the rejection region, we therefore reject null hypothesis, which states that mu is equal to 6 grams. So we can confidently say, or at 99 confidence level, we can say we reject the null hypothesis. Clear? Okay, if that is clear, then we can actually move to the second example. Can we basically move to the second example? And our second example has this to say. So our second example. Always, it is very important to identify which one is your null hypothesis and your alternative hypothesis. So our second example says that the Toyota, let's go. Toyota wants to test a new engine to see whether it meets new air pollution standards. The mean, okay, the mean emission, whenever I find the mean, always the average, right? So the average emissions or mu of all engines of this type must be less than. Pay attention to the question. The question does not say that the mu is 20 per million carbon. No, they are not saying is 20. So in short, they are not saying that mu is equal to 20. Okay. Instead, they are saying that it is less than 20%. So the 10 engines are manufactured for testing purposes. This is your sample size, all right? You collect a sample size of 10 for the manufactured engines to test, and then you find that the mean and the standard deviation of the emission of these samples are determined to be 17.1 and 3 parts per million carbon respective. So that is to say the mean from the sample is 17.1, and then the standard deviation is 3. Okay. So do the data supply evidence to allow the manufacturer conclude that this type of engine meets the pollution standards? Assume the manufacturer is willing to risk a type 1 error of 1%. Now, by the way, type 1 error is same as alpha. Okay, it's equivalent to alpha. So our alpha is 1% or type 1 error. Type 1 error alpha. So we say, now, what you need to understand is we need to begin by selecting first the sample, the parameters, the figures. Number one, you have the X bar, which is the mean from the population, from the sample, sorry. It has been said to be 17.1, right? Then we were told of the sample size that these were just how many? 10 engines. So they sampled 10 engines, X bar. And what do we need? We need the standard deviation. The standard deviation is said to be 3. And then we need the mu. Our mu is said to be less than, not equal. Check. The mu is less than 20. So let's say mu is 20. So our mu is basically less than 20. Less than 20. So now, when you follow this data is not symmetric. It doesn't fall to the right. So when you're forming the null hypothesis, knowing that this is a single-tailed test, the data is just distributed to the left side. So you say that first we form the hypothesis, the null hypothesis. The null hypothesis, H naught, shall be mu is less than what? Is 20. That is what we know. This is what is there in the null hypothesis. So the null hypothesis is H naught, null hypothesis, mu is less than 20, which means that the alternative hypothesis, okay, sorry, like the null hypothesis is H naught is equal to 20. That's what we know. Then we believe, okay, when we test that this mu is less than what? Is less than 20. So our mu is less than 20. Yeah, thank you. So it's less than 20. So the mu is less than 20 in the alternative hypothesis. Okay. So now, from there, we need to go to our test statistics. The test statistic. So from the test statistic, we can observe that this sample size is less than what? Or the sample size is not 6, it's 10. We've said they selected 10. So you're supposed to write 10. So I mentioned 10, but 6. Pardon me for that. So what we do from here, we compute the t-statistics because the sample size is less than 30. T-statistics is given that standard deviation over the square root of what? Of n. So what you do is, what is our X bar? Our X bar is 17.1 minus our mu 20 all over the standard deviation is 3 divided by the square root of 10. And when you do the calculations, if you do your calculations correctly, you will understand or you will observe that the t statistic shall be negative 3.06. When you do calculations, you find that your t is negative 3.06. So this is the calculated t, okay? The calculated t. Just the way how we calculated for the z statistics, now we calculate for the t statistics. The only difference is that the z1, we use it for the sample size that is 30 and above. Now here we are dealing with the sample size, it's less than 30. So that's how you use, that's why you use the t-statistics. We find that it is negative 3.06. Immediately you have found your t-statistic. You need now the t-statistic that comes from the table, the standard normal distribution table. But how do you find the t-statistic from the standard normal distribution table? It is the t alpha n minus 1. Now, why do we actually say alpha, not alpha over 2? Because this data set that we have now is just distributed to the left. If you have checked, they are saying less than, okay, meaning it's just on the left side. It doesn't go to the right side, okay? It's not symmetric. So therefore, just to concentrate on the left side. This data just goes to the left, so it's left it out. That's why you will not have to divide your alpha by what? By 2. So your alpha actually is 0.01, just like that. No need of dividing it. But if it was double-tailed, like the question was asking that the mu is 20, not less than 20. If it was 20 in the alternative hypothesis, then you could have gotten a data that is symmetrically distributed. So that is to say, it could have been on both sides. Then you could have divided your alpha just the same way how you divided statistics. But now you don't divide it because it is just to the left. It's just skewed left. Okay. So basically, what you do here, what you will have to do is you go to the table. You're looking for the point alpha 0.01, comma n minus 1. Our n we said is 10. Okay. Our sample size is 10, so it is 10 minus 1. So it shall be t alpha 0.01. Our alpha is significance level, comma 9, where 9 is the degrees of freedom. The degrees of freedom. Always when you're dealing with the t-statistics, you need the degrees of freedom. Remember now we have already calculated the t-statistic that gave us negative 3.06. Now we need the one that you get from the table. It should be 2 of them. The one that we get from the table, this is the way how we go about it. So we are going straight to the table and check for the area or for the critical t that corresponds to this expression that we give. The t 0.01 alpha, comma 9, the degrees of freedom. So we go and we look for the degrees of freedom. We go to the t-statistic table. The t-statistic table. So the t-statistic table is where? Okay, it's here. Okay, here is the t-statistic table. Then you check the degrees of freedom that we found. It was 9, 9 the degrees of freedom. Then it was comma 0.01, isn't it? Comma 0.01. 9 degrees of freedom, comma 0.01. So you just go upward here. This is where you find your alpha levels. 0.01 is this one. So you find that they meet here. So this number 2.8021 is actually the t-statistic that comes from the table. You just say degree of freedom, comma alpha level. These are the ones that are on top. These are alpha levels. Okay? Just check where they intersect. That's where you get the t-statistic. When you collect your t-statistic like this, 2.821, then you can actually now check how your data is distributed. You can visualize your data. Your data is distributed to the left, like that. is distributed to the left. Then this critic Z, the critic T, we call it the critic T, the critical T statistic will be somewhere here, negative. You give it a negative 2.821. Why should you put negative 2.821? Because the calculated T statistics has got a negative figure. So that's why you're putting everything to the left. So now you compare with the one that you calculated, this T statistic that you calculated was negative 3.06. So we compare in which region this value will lie. The calculated one, the negative 3.06. So you will understand that negative 3.06 will be somewhere here. Okay, it will lie in this region, which we said it is the rejection what? Rejection region. So since this value lies in the rejection region, we reject the null hypothesis. We reject the null hypothesis. That is to say, it is not true that the mu is what? Is 20. Okay. So it is actually the other ones. So basically, that's how you test the null hypothesis. But if you had found that this value is somewhere here, maybe somewhere here, you could have, it could have fallen in the failed to reject a region. So that is to say, you could have failed to reject the null hypothesis. So that is how you make it, the conclusion about the null hypothesis. Any question? We have any question? Okay. So basically, that's how you conclude. Then now, we can actually now do some of these few exercises here. How to find the Z statistic, how to find the, yeah. Let's do number one, the class exercise. The director claims that the average age of a GSP student is 21. This is what is there. This is the first claim, the existing claim, is that the average or the mu is what? Is 21. A new project coordinator at UNZA doubts this claim. Can you set up the null and the alternative hypothesis if the coordinator wishes to show that it is not 21? So the null hypothesis, we already know that our null hypothesis of mu is equal to what? To 21. This is what this is the existing claim. Then the alternative hypothesis will be the opposite, meaning mu is not equal to what? To 21. Mu is not equal to 1. A leading bakery claims that the average cost of producing a standard loaf of bread is what? Is 18 way. If you suspect that the claim exaggerates the cost, how would you set up the null and alternative hypothesis? Question number 2. So what is there already? The belief which is there is that that is called the null hypothesis in question number 2. It is said that mu is equal to what? To 0.80. Okay, 18 way is same as 0.80, right? Where? Okay, this is our null hypothesis. Then our alternative hypothesis shall be mu is not equal to what? To kwacha 0.80 way, meaning mu is not equal to that. Okay, so basically that's about that. So you will understand that all these things now that come, they are just straightforward. They're just the same things, same computations. Question number 3, we just want you to identify the parameters, then you can easily do this. Let's just identify the figures that we used. A stock market analyst claims that the average annual return on stocks is in the construction industry is 12%. You want to test whether this claim is true. You collect a random sample of 6 stocks in the construction industry. can you find that the average annual return is 10% with a standard deviation of 3%? And you can use the 5% level of significance to test the claim. So we start picking values. So we know that our mu, it is said that the average annual return is what? Is 12%, which is same as 0.12. So it's 0.12. That is your hypothesis. Therefore, your alternative hypothesis shall be mu is not equal to 0.12. Then you need the x bar, which is the sample mean. The sample mean. So we are told that you collect a random sample of 86 in the construction industry, and you found that the mean, the average annual return is 10%. So the x bar is 0.10 mean, and the standard deviation is 3%. So the standard deviation is 0.03. Then you are given the sample size n. Our sample size n is what? Is 36, meaning we are calculating a Z-Statistic. We told you that whenever you're dealing with a sample size that is greater than 30, you're dealing using Z-Statistic. And this level of significance, meaning our alpha, is basically 5%, which is same as 0.05. So you have gotten all these parameters. What you need is just to calculate for the z. Our z is found by saying x bar minus c mu all over the standard deviation divided by the square root of what? N. You compute all these figures. The figures are already here. Just compute. Okay. Just get the figures, computing here, find the z statistic. Then from there, you need to find the calculated z. The calculated z, we said this is the calculated z. You need the z that comes from the table, the critique z. The critical z is found by looking at the significance level alpha. And so the significance level is said to be 5% in this question. Since the significance level is 0.05, what you need to do is actually to divide this by 2, since this data is symmetrically distributed as your alpha. Okay, and then go basically to the table. You go to the table to select the z statistics where alpha is equal to 0.025. Sorry, where it is equal to 1 minus alpha over 2. If you find that number, which is basically 0.9750, you basically look for it from the table and move to the left, get the z value, get the z statistics, and compare these two. Which one is it lying in the acceptance region or in the rejection region? So basically, this is what is there about alternative hypothesis or testing of hypothesis.